warm up here. We will get the slide going from current slide. Don't think we started the magnetism chapter, did we?
I don't know.
Oh, you weren't here. You weren't here. That's right. All right, a couple things before we get started. Okay, what I've already said, but I'm saying it again just so it'll be recorded if anyone else needs to hear it. I did get all the grading caught up over the weekend. If you weren't here last week, so you didn't hear this, I have been named to a screening and search committee for a biology instructor, which meant last week every bit of office hours I had were spent screening applications. In fact, I had to take them home with me and screen applications. And when I finally got those finished over the weekend, then I was able to start grading papers. So I got the papers graded over the weekend, but I didn't have a chance to get everything out in Blackboard. Just ran out of time before, now, so there's that. That's my sad song. Now, the other part of that is, because I am on this search committee, we've screened, I think they've narrowed it down to 9 candidates. Only 8 of them, I think, are viable. One, for some reason, the chair decided teaching 7th and 8th grade math was, science was equivalent to teaching college biology. And I don't see that at all, but she said, well, some sort of precedent said it. So I don't know. I cannot understand that one at all. But anyway, the odds are we're going to have to spend at least one day, and hopefully we can get it done in one day. Or if they did it Tuesday and Thursday, maybe 2 days, as long as it didn't shut out one class twice or something. But if they choose to interview on a Monday or Wednesday, there goes another day.
Right.
Did you know about Monday not being a...
Yeah, none of us knew. One of the girls' friends showed up at like 2 o'clock and the gates were closed.
Right.
And so finally we all figured it out.
Right. Well, they sent us an email Thursday afternoon. We aren't here on Fridays.
Right.
Thursday afternoon saying the governor declared it a holiday, a state holiday, so the school will be closed. And I remember noticing at the time that it only sent it to faculty. I said, surely they sent this to students. So I thought, yeah, of course they did, but they just must have sent a different email. They didn't. I didn't realize that until this morning, that they did not send an email. They put it on the website.
Yeah, that's how we figured out
Yeah.
that it was closed.
Yeah, and but like I said, the governor just made the announcement Thursday sometime, and they got the word to us. Actually, what happened is somebody at another school talked with someone at this school, and they asked about it, and then they checked and found out the governor had said that, so then they announced it, but it was quite late coming. And like I said, I should have, at the moment when I saw that, said, did you notify the students? But I just assumed they would.
Yeah, because I looked on Blackboard for like an announcement or anything, just in case, and I was leaving to come here when somebody one of the girls in her class messaged us and was like, hey, no school today. I was like, you just saved me an hour drive, so I appreciate it.
So sorry about that. It's I think inexcusable, but I'm sorry. I should have said something, but I just assumed they had it. So anyway, sorry that happened. All right, let's get on with the subject. Topic 19. The book calls it Topic 19, the current edition. The previous edition is called the Chapter 19. It's on magnetism. Okay? Now, magnetism is one of the most important fields of physics in terms of applications. It's been around forever, okay? Magnetism is closely linked with electricity, and we'll see the correct link before the end of the chapter. But to start with, magnetic fields affect moving charges, okay? That's a given. If you have a fixed magnetic field and you have a charge moving through that field, unless it happens to be going in one particular direction, it's going to be affected by that. If it's along the tree, it isn't. Moving charges also produce magnetic fields. Okay? We'll talk about that a little bit later. Changing magnetic fields create electric fields. And they should have put one more statement here: changing electric fields create magnetic fields. That would have completed everything, but they didn't put that last one in. There was a Scottish physicist, a brilliant guy, obviously. Now, it looks like his name would be James Clerk Maxwell, but you know the Scots pronounce things differently. It's pronounced Clark. James Clerk Maxwell first described the underlying unity of electricity and magnetism in the 19th century. And how he did this is pretty amazing. There are, I think it's a set of 4 equations called Maxwell's equations. And he came up with them basically out of thin air. I mean, he didn't. He really studied and put them together. He had no, they were all theoretical. He didn't have the equipment or anything else to test them. It was probably, I'm guessing, 40 to 50 years after he came up with this that finally we had the equipment that we could actually put these to the test, and those 4 laws worked perfectly. So it's really a brilliant guy to come up with the theoretical framework for it long before we had the means to verify it. So what are magnets? Well, we're going to be talking about that the whole term. What are some characteristics of magnets? Magnets are always polar. The poles of a magnet are the ends, so to speak, where the objects are most strongly attracted. Now, just because our Earth itself acts like a magnet, okay? And near our rotating true north, but not near it, not on it, but near it, is the magnetic North Pole. And because every magnet you'll ever see will generally point toward the north and toward the south, you know, one end of it to the north and one to the south, that's what they named these 2 poles, the North Pole and the South Pole of a magnet. Okay? Now, here's one of the other characteristics. Number 1, magnets have poles. Number 2, like poles repel each other, unlike poles attract each other. Okay? Very similar to electric charges. Electric charges, like charges attract, unlike charges repel. Okay? Magnetic poles cannot be isolated. You can isolate a charge. You can have a positive charge sitting here with no negative charges anywhere around. You can have a negative charge anywhere with no positive charges anywhere around. You cannot have an isolated either north or south pole. Let's say you had a bar magnet, right? And that would be the north seeking pole, that's the south seeking pole. What if you say, well, I'm going to break this off so I isolate the north pole? What happens? The moment you break it, this end of that becomes the south pole, and this end of this one becomes the north pole. You can never, no matter how small you break it, ever get it down so you have a monopole. A magnetic monopole does not exist. If a permanent magnet is cut in half repeatedly, you'll still have a north and a south pole in every piece of that. This differs from electric charges that you can isolate a positive charge, you can isolate a negative charge. That can happen. You cannot do it with magnets. There is some theoretical basis for monopoles, but none have ever been detected. I don't know what that theoretical basis is, but it's all theory. None have ever been isolated or detected. Moral magnetism. Now, they sort of left off something here. I'm going to go and throw it in here. There are only 3 naturally occurring magnetic materials, elements. Okay? And you don't have a book here with you, but in the back of the book is a periodic table. Okay? And if you find iron on that periodic table, it's right here. It's element number 26, atomic number 26, and it's one of the transition metals here. Okay? And right next to it is cobalt, and right next to it is nickel. Those three are the only three naturally occurring magnetic materials. Okay? The only three. So they start with this: an unmagnetized piece of iron, one of those magnetic materials, can be magnetized by stroking it with another magnet or stroking it on another magnet, either one. You have to have contact, and you have to have friction. You have to have disturbance, okay? The stroking. You can't just get it close to it and do like that. It will not become a magnet, okay? But if you touch it and rub it, stroke it on the other magnet, or vice versa, then you can create a magnet if you have the magnetic material. It's somewhat like stroking an object to charge it, okay? Like rubbing amber with silk or something like that. That will may charge one of the materials. Magnetism can be induced, okay? If a piece of iron, for example, is placed near a strong permanent magnet, it will become magnetized, okay, at least temporarily, okay? So if you have a very strong magnet here, okay, here's the north pole of the magnet, extraordinarily strong. Bring a non-magnetized piece of iron, or nickel or cobalt, iron or cobalt, close to that strong magnet. That's going to attract the negative poles of this, and that will make that be a positive. So you can induce magnetism there. If you don't touch it and then separate them, then this piece goes back to being non-magnetic. Okay? If you perturb it in some way, then while it's in the presence of that strong field, then it does become magnetized. Okay? Before we go there, let me give you sort of a dumb example, but it really did happen to me. All right, so I need to come down from the computer lab, or up from the computer lab, right? Okay. All right. I forgot to ask this of the first class. Did you come Monday?
This Monday?
Yeah.
No.
You didn't? Okay. Did you know already it was a holiday, or you weren't planning to be here anyway?
I just checked the website.
You did? Okay. Yeah, they say check your email. They didn't put it on the email. I don't know why they didn't.
But some people were saying that it was closed, so I checked
Right.
the website.
Right. Good deal. Thanks. The other thing, I meant to say this in the last class, and I forgot it there too. And you weren't here, so you wouldn't have heard any of this. I'm sorry, I'll be repeating it because I don't know if you'll go back and listen to the first part or not. A little over a week ago, I was assigned to be on a biology screening and search committee, okay, which is a real pain in the neck because we had something like 18 packets to go through to screen for this biology position. And that took a long, long time, especially since the day they said we should do it was last Monday. Not this Monday just happened, but the one before that. And I even held back and said, look, I've got class from 8 o'clock in the morning till 9 o'clock at night. I have no time on Monday. Can I come Tuesday after 3:30 to screen? And they said, sure, if it's all right with Human Resources. Human Resources said, fine, do it. So I went Tuesday afternoon, got there a little before, or right around 4, and went to start screening. And they said, oh, we're doing the screening differently now. it's all online. You didn't have to come down. I said, well, why did they say we had to be here Monday? And they gave us 2 choices of time to do it. And they said, well, I don't know why they said that, but you didn't have to be here. So I just wasted half an hour driving. I could have been screening in my office. Except then when she tried to get me on, because it's all online now, they put all the packets online, that I couldn't get online because the system wasn't working. So I sat there, and it was about another hour or so before they got that working. So finally they got it up so I could look at it, and then I had time to screen 3 candidates before the woman had to go home. So she sent the packets home with me and said, you can do it at home because you can, screen it online. So I took them home, and for the rest of last week, I did nothing but screen it anytime I had office hours. Of course, I don't have any office hours Monday or Wednesday, only on Tuesday, Thursday. But every chance I had, I was screening candidates. I took them home and out of town, and I was doing that all during the break. And because of that, I didn't get any of your grading done until I finished all the screening, which was into the weekend. So I got your grading done, but I didn't have a chance to put it on Blackboard. So if you're looking for grades on Blackboard, you won't see them unless they were done earlier. All right. Here. Yeah. Pardon me? Okay, you didn't take it before you left?
No, I didn't.
Okay.
You told me that we did 1 and 201.
What's that?
We did 1 lab in 201 and 1 lab in 202.
Okay, you did the on-ball lab.
Yeah.
Okay.
I'm just talking about last week when I wasn't.
Electric circuits lab was the one you don't have, right?
Yes.
Is
And,
that right?
did we have a lab in 201?
I don't remember.
I can wait.
Okay, I know you did the projectile motion lab. Did you do the friction lab?
I don't remember. What was the friction lab?
It was a friction
With
for
the
the
ball
inclined plane.
And the
you,
ball?
no, not ball. Blocks of wood.
No.
You did not do that.
No, I did not.
Okay. Here's the friction lab.
No, I did not do that. That was it?
Yeah, you got the test, didn't you?
Yeah.
Okay.
Do I have to get this from somebody or make it up? Or?
I guess so. I mean, it's, whatever you can do. I just don't have lots of time on Monday, Wednesday. I have some time on Tuesday, Thursday. But yeah, you'll probably need to get with someone. So anyway, that's why everything that you've turned in so far has been graded, but it's not on Blackboard. Here's the other problem, is that they may still have us interview. We're down to 9 candidates, and they may have us interview someday in a coming week. The bad news there is, if they do it on a Monday, Wednesday, we lose another day. And we've already lost 3. Memorial Day was a Monday. I had to go to New Orleans on a Monday because they scheduled a meeting that I had requested to go to on a Friday, Saturday. They scheduled it in Atlanta. They scheduled it in New Orleans for a Monday, Tuesday. And then last Monday was a surprise, no school then. So we've already down to an 8.5-week term rather than a 10-week term. So I hope they don't do it again. All right, so let's get on. Okay, here was my dumb story about this. when we moved into the house where we currently live, behind our garage was a shed. It was a ramshackle shed. It was leaky. It was uneven. It was rotting. It was termite infested. It was not much of a shed. You couldn't store anything in there that was any value because the shed leaked. And then from the shed, that was attached to the back of our garage, and then from there on back, they ran a privacy fence up to the corner. But when we purchased our property, the house and the property line was a good 4 feet toward the neighbor from where that was, because they just used the back of the garage, and did the shed and the privacy fence from there. Well, I had to tear down the shed. It was no good whatsoever. And then the privacy fence was not in great shape either. And I thought, if I'm going to have to do a new one, I should put it on the property line. And I talked with the people who lived next door. They were renters, but they talked with the owners and said, oh yeah, the part of our yard is their property. So they said it's perfectly fine to move the fence. So I tore down the shed and was in the process of moving the fence. It was a hot, dry summer, and I was having to dig fence holes in hard red clay. Nothing like we have this summer with lots of rain. It was miserable, okay? Shekinah is here. Okay? Now, what I had done, I put a post at either end. I measured it on the property line, got it lined up with that, and put a post on either end, and what I was going to do was run a really tight, taut line between the top post and the bottom post. I had those set. And so what I was doing was driving a nail into the top of that post that I had set. Okay? Now, I was reaching above my head because that was way up on the hill, so I had to be at pretty much the top of the post here to come down and be able to line my post up with the other holes I was going to dig. So I was up here nailing, and I'm not a very good hammerer, and I hit the hammer several times. But by the way, our property line runs almost directly due north. Okay, north-south. So I was nailing the nail in the top of that post, and after several strokes, I missed where it hit, and the nail went flying. Well, the grass was there and stuff, and I reached down, and I happened to have the hammer in my hand, and I reached down, and I was just looking for the nail among all the leaves and the grass and stuff, and suddenly the nail attached itself to the hammer. I went, what in the world happened here? And of course I thought about it for a minute and said, of course. I was nailing the nail basically due north, hitting it with the hammer. Okay? The Earth's magnetic field lines run north to south, right? Well, I was perturbing the iron in a strong, not a strong, but in a magnetic field, the Earth's magnetic field, and I was banging on it, and that made both the hammer head and the nail turn into little magnets. And that's why the nail was attracted to the magnet. Because if you perturb a magnetic material in the presence of a magnetic field, that's just like stroking it on another magnet, you will make it into a magnet. It wasn't a very strong magnet, but it just pulled it to it. Okay? So it did become magnetized. All right, let's look at the types of magnetic materials. And I've already mentioned some of these before, but we'll mention them again. The soft magnetic materials, such as iron, are easily magnetized, and that's what that nail was. But they also tend to lose their magnetism easily. They're easy to magnetize, but also easy to demagnetize. The hard magnetic materials, and that has nothing to do with the hardness of the metal, is how hard it is to magnetize. They are difficult to magnetize. they tend to retain their magnetism. And by the way, what were the three magnetic materials?
Iron, cobalt,
5 cents.
nickel.
Nickel, okay, good. Iron, cobalt, and nickel. Cobalt and nickel are your hard magnetic materials. Iron is your soft. Iron is not soft, but it's easier to magnetize. But the hard magnetic materials are harder to magnetize, but they're also retain their magnetism more easily. Okay? And we'll take advantage of a couple of those facts later too. Now, what are the sources of magnetic fields? Here's something to catch and hang on to. Please. The region of space surrounding a moving charge includes a magnetic field. Okay? In other words, a moving charge induces a magnetic field. The charge will also be surrounded by an electric field. Okay? If you have a charge, it's already surrounded by an electric field. What's the rules for the field around a electric charge? Field lines point where? Away, we're talking electric now, away from a positive charge toward a negative charge. Okay? Those are the electric field lines. Okay? That charge by itself will not induce a magnetic field unless that charge is moving. If the charge is moving, then you induce a magnetic field. The charge also, of course, will be surrounded by an electric field depending on whether it's a positive or negative charge, like I just described. The magnetic field surrounds a properly magnetized magnetic material. Okay? Rather strange way to say it. Properly magnetized magnetic material. So the magnetic field, and there are rules for that too. Let's go into those rules. Okay? Magnetic fields, like electric fields, are vector quantities. Okay? Now, I apologize for the slide here because they used this big capital B here, and it messed up the tail on the Y here. So that should be a quantity there with a Y. The way it reads, it's just a quantitative or something like that. That's a Y there, not a V. Well, let me get my pen activated in a dark color. That is a Y. Okay. A vector quantity, and the symbol for it, what's the symbol for an electric field? Anyone remember? Symbol for electric field. Electric. Symbol. Capital E. And it's a vector quantity. So just like this is a capital B, it would have been a capital E. The electric field is capital E. The magnetic field, why, I don't know, but it's a capital B rather than M or something else. It's a capital B. The direction is given by the direction that a north pole of a compass needle would point if you were placed at that location. Okay? So when I was hammering on that nail and happened to be hammering almost due north, okay, then that nail was pointing in the direction of the north magnetic field lines. So therefore, it was in line with that, and when I banged on it, it made a magnet in that direction. Okay? So, and of course, the compass needle point would point in the direction of the toward the north pole of the Earth's magnetic field line. Okay? The magnetic field lines can be used to show how the field lines, as traced out by a compass, would look. And I think that should be your next slide. Yeah, here it is. This is the figure at the bottom of page 621. Now, there is an interesting figure, 19.1 at the bottom of page 620. I thought they might say something about it, but they don't. So let me go back and do it. This is a rail gun, launches projectiles at high speeds using magnetic forces, not explosives or anything else, magnetic forces. Okay? Larger versions could send payloads into space or be used as thrusters to move metal-rich asteroids from deep space to Earth orbit. In this photo, a rail gun at Sandia National Laboratory in Albuquerque, New Mexico, fires a projectile at over 3 kilometers per second. That would be about almost 2 miles per hour. No, I'm sorry, 2 miles per second, okay? Almost 2 miles per second, which is incredibly fast, okay? Now, here's the second figure. This is 19.2. This shows a north-south magnet, right? Now, if you were to place a little compass here, say you place a compass here, of course the north pole of the compass will point away from the north pole here because the south pole of the compass will be attracted to the north pole here, right? Opposite poles attract, right? Okay? If you move it around here, then the north pole starts pointing in different directions because the north pole is always trying to get to point to that south pole, but then the south pole is being attracted to the north pole, so it doesn't let it go immediately to turn there, it turns gradually. Those lines that you trace, when you put those imaginary compass needles in there, this creates your force lines, your magnetic field lines, okay? And this is what it looks like if you remove the little magnets. The compass can be used to show the direction of the magnetic field lines at A, and the sketch of those field lines at B. Does that make sense? Anybody? Okay. Now, well, sound divided to show up today. Good. We can almost picture, come really close to picturing what magnetic field lines look like, at least in 2 dimensions. You can almost do it in 3 also. If you take a piece of paper and place under the piece of paper a bar magnet like this, and then sprinkle iron filings on top. If you do this, you'll see that the fields, the iron filings are, and here's Megan. Do you know if Tia's coming today? She's not. I thought I heard she was going to be out. Okay. The iron filings will line up basically almost along those field lines, just like you see here. No one put them here. They just sprinkled them over that gently, and this is what you get. Okay? They show the pattern of the magnetic field lines. And notice the field lines are much concentrated around the poles of the magnet and hardly any concentration in between. Okay? The other thing is the field lines bend around. You can imagine putting little compasses here and they would follow these field lines just about exactly. Okay? And that's what the field lines look like. The direction of the field is the direction the North Pole would point. So I just did my hand the wrong way. They would point this way because they always point away from the north toward the south. So the field lines go like this. All you see are the field lines here, and you don't see the direction of it until you picture or mentally put a little compass there along that field line that always points away from north toward the south. Okay, does that make sense? All right. Now, What if you have two unlike poles? A north pole here and a south pole there. Okay? Sprinkle iron filings over that. Now, of course, in between, compass needle would point away from the north toward the south. So that's the direction of the field lines here. As you get further out, they bend more and more and more, always like this, until you get way out there, and then this one bends, the field lines then go back to this south pole, and that one goes back to this north pole. But the concentrations are right there. And right in between, they're almost parallel field lines. That's called a uniform field. Very uniform right in between those two strong poles. Okay? The iron filings are used to show the pattern of magnetic field lines. The direction field is, yeah, we've already said all that. Well, no, we haven't. Okay. Iron filings are used, we said that part. The direction of the field is in the direction the North Pole would point, if you had a little compass there, which way would north point, away from north toward south. Okay. And compared to the electric field produced by electric dipole. Remember what electric dipole was? That would be a plus charge here, a minus charge there, and the field lines would be fairly uniform in between, bending around like that. That looks almost exactly like you would have with an electric dipole. So you see, electricity and magnetism, we knew already, and we know, we use it all the time, they're related, but boy, how closely related. That looks just like the field lines of an electric dipole. Okay, what if you had two similar poles, like this? Okay? Well, again, these are two north poles now, and most of the concentration is around the pole, so you have heavy concentration there, but look at where the field lines are going. They're going away from each other, because this one goes up this way because it's trying to get away from the north here, so close, but then as soon as it gets here, it's trying to go away from that. So the field lines bend like this and bend like that. Now here's a couple more things to note. Notice these field lines never, ever cross. They always go in one direction, and they never can cross like that, ever. No matter whether you got a single magnet, two opposite poles of different magnets, or two similar poles of different magnets, they almost look like they collide here, but they never cross. They flatten out and go out and around again. Okay? So that's another thing, and that was also true about electric field lines as well. So what's the symbol that represents electric fields? What was the symbol that represents electric fields? Capital E, and it's a vector quantity. How about magnetic fields? What symbol represents magnetic fields?
Capital M.
No, a good guess, okay, but it happens not to be. Capital B, and it's a vector quantity. Why, I do not know, but it's not M, it's B. All right. Moving on to the Earth's magnetic field. Okay? And we already talked about this a little bit. The Earth's geographic North Pole is fairly close to a magnetic South Pole, okay? Or equivalent to that. Here's a little bit of a problem with how we name these, okay? We know that's the North Pole of the Earth, right? Where the axis is, okay? It spins a certain way here, like this, and that's the North Pole, that's the South Pole. True north. Okay. Now, we named poles on a compass by the one that points north. We said it was north. But what direction does a compass needle point? The North Pole of a compass needle is attracted by what? the South Pole. So that means the Earth's magnetic North Pole, we call it, is really acts like the South Pole because North Pole point toward it. Okay? So, I'll show you where it is. This is what it has it. It's hard to see, but if they don't do it. There's the North Magnetic Pole right there. It's something like 80 degrees north rather than 90 degrees north. Maybe 82, but just shortly over that. It's in the upper part of Canada, well inside the Arctic Circle. The Arctic Circle is right here, so it's closer to the North Pole than the Arctic Circle, but it's not right on the North Pole. We'll talk about that a little bit later. But in reality, it acts like a South Pole because North Pole point toward it. Now, the South Magnetic Pole is a bit further off, okay? It's down here just off Antarctica, but it's about 66 degrees south, not even like the North Pole was in the near 80 degrees north. This is 66, so it's way off, okay? You would think it would be down here. It's really up here. Actually, just outside the Antarctic Circle, which is bizarre to me that it would be that far off. There's the South Magnetic Pole, and here's the North Magnetic Pole. Okay? Realizing this is acting more like the North Pole, this is acting more like the South Pole. Okay. That's why they say that. So, if you really had the Earth's geographic South Pole corresponds to the North Magnetic Pole, so strictly speaking, the North Pole of a magnet should be called a north-seeking pole, not a North Pole. So everybody calls it the North Pole. It's a north-seeking pole because it's pointing to the north. That would make it a South Pole, but they call it north-seeking pole. South Pole should be called a south-seeking pole because it's seeking the pole that's in the south, which would make it then truly a north. And here's the figure that's figure 19.4. And they've already said the little tip there, so I'm not going to repeat it. The Earth's magnetic field resembles that achieved by burying a huge bar magnet deep in the Earth's interior. Okay? Of course, you can't really do that because it would be melted in the middle, for sure, because the Earth's outer core is molten. So you couldn't really have one, but that's what it acts like. Okay? Now, there's a couple of features there that are important. Okay? One, as I already mentioned to you, the axis of rotation, which is true north here, is actually 11 degrees off. So I said it was about 80. It's really 79 degrees north. So it's about 11 degrees off the magnetic axis, and the actual axis of rotation is about 11 degrees off. Not bad, not much, but a little bit. Okay? Now, here's the other thing. Field lines near the equator do point truly north and south. Okay? Field lines north of the equator, actually, they have a component pointing north, but they also have a component pointing down into the Earth. Because the Earth is a sphere, and if you're standing here on the sphere, the South Pole is that way, into the ground. It has a component in the north direction, but it basically is up. It gets even stronger if you get up near that, then it's pointing almost straight down. Okay, so there's a downward component as well as a north-south component. So keep that in mind as well. Okay, I think we beat that to death. Any questions on that? The magnetic equator and the actual geographic equator, again, would have about 11 degree difference. Not that anyone really matters about the magnetic equator. Okay. Now this is what I was talking about, the dip angle. I didn't use that name, but it is. If a compass is free to rotate vertically as well as horizontally, it points into the Earth's surface, okay, toward the Earth's surface. It doesn't point, okay. I do this a lot in some of my classes. They'll say, someone point to the north, and if they have a good sense of direction, they'll do like that. No, that's not really. That's pointing out in space, because you're on a globe, and you're pointing out in space. North would be down that way, okay, because the actual North Pole is that way. You have to take into account the curvature of the Earth. Same thing to do with the magnetic field lines. If you have it fixed in something that's horizontal, yeah, it's going to point that way, but if you let it flow three-dimensionally, it's going to point like that. It has a component in this direction, but it also has a component down. That's called the dip angle. Compass is free to rotate vertically as well as horizontal. Points there. The angle between the horizontal and the direction of the magnetic field is called the dip angle. Okay? As opposed to dipstick. No, that's never mind. Okay. The farther north you get, then the farther from horizontal the compass needle would be, until when you were standing right on top of the north magnetic pole, it would be pointing straight down. Straight down. You wouldn't have any idea because you're at the north magnetic pole. Okay. Compass needle would be horizontal at the equator, and the dip angle would be 0. Anywhere else, north is going to be dipped down, south would be dipped up. Okay. The compass needle would point straight down at the south magnetic pole, and the dip angle would be 90 degrees. Okay, it would be at both of the poles like that. And that would be at the magnetic poles, not at true. Okay. The strange thing is, if you're at the South Pole, the actual real South Pole, your compass needle would point that direction was south. Okay. If you're going, the only direction you could be is going north, and yet that would be pointing south in that direction, because the south magnetic pole is there, so that acts like the North Pole, so it would be saying south was in that direction, and you're on the South Pole. So the north would be pointing toward you, and that, of course, would make no sense at all. Okay. Same thing when you're on the North Pole. The true North Pole, it would be pointing north, would be somewhere south of you, which, of course, makes no sense. Now, the dip angle of 90 degrees is found at a point just north of Hudson Bay in Canada. Okay, and that's where I was pointing to before. Here is Hudson Bay, and you go due north of that. So hard to see here. Actually, not quite due north, a little bit west of due north, and you hit the true magnetic. The magnetic. Okay. So that dip angle of 90 degrees is found at a point, it says just north of Hudson Bay in Canada. It's considerably farther north. Yeah.
Aren't they always changing?
You're absolutely right. They tend to move around some. Okay? And we'll talk about that a little bit later, the reasons for that. And they say this is considered to be the location of the South Magnetic Pole. The reason they call it South Magnetic Pole, our magnets, North Poles of the magnets point to it, and that would be pointing to the south. Okay? The magnetic and geographic poles are not in the same exact location. In fact, they're nowhere really all that close. 11 degrees, that's not bad, but you know. The difference between true north and the geographic North Pole and the magnetic North Pole is called the magnetic declination. Now, in astronomy, declination means something else, but it's not too far up from it. The amount of declination varies by your location on the Earth's surface. Now, you're absolutely right, they do sort of wander around, they drift some. I don't know if it's a regular kind of drifting, and I've not read too much about it. the strange thing is, to me, one of the strangest things going, is the north and south magnetic poles have flip-flopped about 22 times. Now, I don't think it was a sudden thing, else everything would be totally whacked up. I think it's a very gradual thing. And I think what's happened, the magnetism, this is just my opinion, I've never read this anywhere, the magnetism varies very slowly. And at some point, the magnetism almost goes to zero, but then when it comes back again, it's going back in the other direction and goes like this. So I think it's this kind of a deal, not a very sudden change. Now, I may be wrong, but that's what it seems like to me, the only explanation I can give. So yeah, that would mean it does change and it does vary. But we'll talk a little bit later about why that's true. I think this is what goes over. If it doesn't, ask me and I'll try to bring that up. Okay. So that difference there is called the declination. The amount of declination varies. Okay, here's what I was going to show. If you were on the line directly between the true north and the north magnetic north, on a line through that, so say a straight line, a great circle through that, going down through here, then anywhere along that line, your compass needle would be pointing to the north magnetic pole, which is what we call the south magnetic pole, which would be in line with the true north, so your compass would be telling you absolutely correct. But if you get off the ways here, now your compass needle points there, where true north is there, that difference is called your declination. Okay? So depending on where you are, the declination varies, sometimes pretty extremely. And here is the approximate lines for this. And you see even these are wavy lines, okay? Other things come into play. That zero line almost forms the border between North and Georgia and South Carolina. I mean, it's just uncanny that that is a zero line. I grew up just south, most of my growing up was just south of Augusta, Georgia, right here. So I was almost at 0 degrees declination. My compass, if I had a compass, it would point almost due north. Okay? Here in Birmingham, or Bessemer, right in here somewhere, we would be, well, it looks like maybe about 3 degrees off. Not bad at all. Okay? We're pointing east of where true north would be. Okay? Up here in Cape Hatteras, North Carolina, you're about 10 degrees west. Here around New Jersey, 15 degrees west. Boston, about, I'm sorry, the hell's too many lines there? 0, 5, 0, 5, this is 10. So New Jersey would be about 10. Boston would be about 15. And Nova Scotia, or Maine, Portland, Maine, would be close to 20. Going the other way, what would that be? Gulf Shores, right around 5 degrees east. That's pretty close to Austin, Texas, I would guess. Oklahoma City, that would be about 10 degrees east. Over here, San Diego, not far off from 15 degrees east. Up here, the California-Oregon border, boy, what a strange line there, about 20 degrees east. Okay? So, yeah, in the U.S., you have a lot of variation. Just happens to be we're right on the zero line, not too far from it, so we don't have a lot of declination error in our compass readings. Now let's look at the source of the Earth's magnetic fields. From one of the very early slides, what creates a magnetic field? I think I've said this before. What creates a magnetic field? Okay, a moving charge. Yes, a changing electric field, basically a moving charge. There cannot be large masses of permanently magnetized materials since the high temperature of the core, okay, they've left out a whole lot here, prevent materials from retaining permanent magnetization, okay? That's what we're talking about near the center of the Earth. Yeah, it just isn't going to happen there. The most likely source of the Earth's magnetic field is believed to be electric currents moving charges in the liquid part of the core. Now, let's just go through a little bit of how they think the Earth is formed. At the very core of the Earth, it is solid, mostly because of the enormous pressures from above. It's so high a pressure, it forms a solid. But then the outer core is liquid, okay? And because the Earth is spinning, okay, the Earth is always spinning, constantly spinning. That outer core there being liquid, it doesn't have to spin as fast as the Earth does because it's liquid, right? You can spin a glass of water and the water basically stays still except that right around the edge of the glass, okay? Same thing's happening inside the Earth. So the Earth is spinning around this liquid outer core, okay? So as it's spinning around, there's friction there, okay, between the mantle, which is solid, and the outer core, which is liquid. There's a little bit of friction there, okay? Neither one of those are really smooth surfaces, so there's going to be some friction, and that creates currents moving around because electrons are knocked off by the friction. And those moving charges induce a magnetic field, okay? So the most likely source of the Earth's magnetic field is believed to be the electric currents in the liquid part of the core, okay? That's the outer core. Probably that liquid part closest to the mantle, which is the inner part of the solid that's underneath us, okay? We're in the crust, and then the mantle is a really thick layer, and then the mantle gradually becomes liquid core, so it's an integrate there, okay? And that's probably what creates the electric currents. Now, the part I don't get, and I cannot wrap my head around at all, since the Earth is spinning in the same direction, why is the magnetic field flipping? That makes no sense. Unless there's some sort of eddy currents going in there, and they sort of do this and then turn like this. I don't know. It really makes no sense. I can't figure it out anyway. Must make some sense. Okay. Now, there are a couple of applications they talk about here. They talk about magnetic bacteria. So if you're in biology or a biological field, you'd probably find that pretty interesting. And then the labeling of airport runways, they always do those magnetically, not true north. So if you realize that, because your gyroscope compasses could go down, so you always line up according to the magnetic compass, which should be true. There is a interesting little Applying Physics 19.1, compass is down under, and everything should be fine there too. Now what they don't do, I don't see it here. Oh, here it is, sorry. I jumped ahead a little bit. An interesting fact, this is near the middle of page 623, the upper part of the middle of the page. An interesting fact concerning Earth's magnetic field is that its direction reverses every few million years. Why? I don't know. Evidence for this phenomena is provided by the basalt, that's the iron-containing rock that usually is in the bedrock at the bottom of the oceans, okay, made by magma that has deposited there. Evidence for, that is sometimes spewed forth by the volcanic activity on the ocean floor. As the lava cools, it solidifies and retains a picture of the direction of the Earth's magnetic field, and when the basalt deposits are dated, they provide the evidence for the periodic reversals of that field. The cause for the field reversals is still not understood. I don't know if anyone's come up with a good application of that. The origin of those reversals, not understood. The direction of the Earth's magnetic field reverses every few million years. Well, think about that. Yeah.
How do they know it reversed?
Say again? How do they know it reverses? Because they drill down and take core samples of that basalt. And you see, I was explaining this earlier before you came in. When there's some sort of perturbation in the presence of the Earth's magnetic field, then if you got iron, nickel, and cobalt, and since basalt is largely iron, which is a soft magnetic material, not that iron's soft, but it is easily magnetized, and when say right now, if there was a volcanic eruption and it laid down a layer of lava, and some of that a lot of it was in this direction, then those field lines would be pointing like this, a uniform magnetite, an iron ore that is magnetic, naturally occurring, it's called lodestone. It would be this way. But somewhere down about a few million years ago, there's another layer that is magnetic. It's going this way, and below that, and below that, and below that. And these eruptions have been happening. Are you familiar with plate tectonics? Okay. Down in the middle of the Atlantic Ocean, they call it the Mid-Atlantic Ridge. Actually, Iceland sits right on it. Okay, and it basically goes down just about midway between the continents here. There's sort of a jagged sort of line there. And there, the plates are spread. So there's always magma coming up there. So when it reaches the surface, it becomes lava. And it cools. And when the Earth's magnetic field lines are fairly strong, they form here. Well, at one time, the theory is there was one huge continent, and it's slowly been spread. So out here near the shoreline here is old deposits, and they drill down there and they see where it's alternating, and they go and they run it all across the Atlantic, and they find that pattern on either side. They mirror each other, and the reversals mirror each other perfectly as they go down. It is phenomenal.
So how is Pangea a theory if that's like pretty hardcore evidence?
What's that again?
How is Pangea a theory if that's pretty like hardcore evidence?
It's pretty well respected. The reason it's called a theory and not a law is that you can't reproduce it. You have to be able to prove a theory. And how can you reproduce that? You have to start over again so that it's happening. No, the evidence strongly suggests it's correct, but you can't go back and test it again. Sort of the same reason some people say the theory of evolution is just a theory. Others say it's a fact, but no, you can't go back and recreate all that, that I know of anyway. So, the big key here, we don't know why. But you see, if they're millions of years apart, how long has mankind been using magnetic materials? Not long at all. What? no more than 10,000 years at least, and that compared to a few million is a tiny percent. We've all been living in this one thing. Now, the Earth's magnetic field seems to be weakening very slowly, and as it weakens, it could be, and I think it is, there'll be a time when there is no magnetic North Pole. But then when it comes back, it slowly gets stronger, and I think the direction is reversed. Now, I don't have any basis for that. That's the only thing I can think of, reason for that to happen. Okay, let's move on to magnetic fields, 19.3. When a charged particle moves through a magnetic field, a magnetic force acts on it. Okay? So let's say we have a magnetic field. This being a north pole of the magnet, this being a south pole. So the field lines would be pointing this direction, away from north toward the south. If a charge moves through it like this, the charge gets deflected depending on whether it's a positive or negative charge. Okay? When a charged particle moving through a magnetic field, a magnetic force acts on it and bends it. This force has a maximum value when the charge moves perpendicular to the magnetic field lines, and 0 when the charge is moving along the field line. So if you have the field lines like this, and the charge is moving like this, no deflection at all. And they're moving like this, maximum deflection. Okay? Now, one can define a magnetic field in terms of magnetic force exerted on a test charge moving with in the field with a velocity v. And whoever the typesetters here, it's rather bizarre that they can't just bold that v and keep it on the same line, but maybe it's the error, I don't know. It just seems to be a little bizarre. But that v is a vector, bold, velocity, arrow over it. Similar to the way electric fields are defined, one can define a magnetic field in terms of the magnetic force exerted on the test charge moving in the field with a direction with a vector v. Similar to the way the electric field lines are defined, the magnitude of the magnetic force is, now here's the magnetic force. Get this. Q V B times the sine of the theta in between the velocity and the field lines. Okay? Q is the amount of charge. Okay, remember we said a test charge. That would be the amount of charge on it. V is the velocity of that field. Right now we use that as the magnitude of velocity or speed. B is the magnitude of the magnetic field line. Remember that was our B, magnetic field. And sine theta is the angle in between the velocity vector and the field vector. If that is 90 degrees, then this is the maximum. Sine of 90 is 1. If it's 0 degrees, sine of 0 is 0. So there is no force acting on it. So that is QVB times the sine of theta. It gives the magnitude of the field lines. The actual equation is divide this side by QV sine theta, and you get V here. V is equal to that force divided by QV sine theta. And that's why they said this is how you can define the magnetic field in terms of the force that you sense, the charge that is of your test charge or whatever charge you're dealing with, velocity of that charge, and the sine of the angle in between. This is how we define the magnetic field V. That would be the values. Let's take a look and see what the units will be for that. Okay? Force, what's the unit for force? Newton. And what is a Newton in basic units? Mass, kilogram, times acceleration, meters per second squared. That's what a Newton is. Q is? Charge. And what's it measured in? Coulombs, very good. V, velocity, what's it measured in? Meters per second. And of course, sine theta has no unit. So this meter cancels out that meter. This second, I'm sorry?
Degrees.
Pardon me?
Degrees.
No. Okay. The angle may have a unit of degrees, but sine of an angle is a dimensionless quantity. Because what it's doing is a ratio of, sine is a ratio of opposite to hypotenuse, and whatever those are, same dimension here and here, so it's a dimensionless quantity. So trig functions are dimensionless quantities. The second cancels out one of those seconds. So what we are left with, the unit for magnetic field would be a kilogram per Coulomb second. Kilogram per Coulomb second. That's a capital C, by the way. Okay. Rather strange unit, wouldn't you think? Well, a Newton is a kilogram meter per second squared. Get it down to the basics. This is a Coulomb, and that's a meter per second. That has no units. So this meter cancels out, and that second cancels one of those, and you're left with a kilogram per Coulomb second. Rather bizarre measure for a field. Actually, that's not what we use. We would use a Newton per Coulomb meter. A Newton second per Coulomb meter, which would be rather strange itself. Okay. But anyway, they're not asking you for that. F is in newtons, Q is in coulombs, V is meters per second. The SI unit for magnetic field is called a Tesla. Capital T. Why? Who? Nikola Tesla. Very good. What was he known for?
Crazy experiments.
Second?
Electricity.
Yeah. With whom is he usually associated? He actually worked in his lab.
Ben Franklin.
No, later than that. Thomas Edison.
Yes, that's what.
But,
Isn't there a car named after him?
yes, the electric car. Exactly. But that's like a Ford, Chevy Impala named Tesla. This is a unit, Tesla. Actually, it's made up of kilogram per Coulomb second, which is rather strange. But that is the SI unit for magnetic field, Tesla. Okay. Here's how we really do it. Okay. Forget this. Newton per. Let's go back to here. Okay. Coulomb meter per second, right? A Newton per Coulomb meter per second. Well, change the per second to be over here rather than there, and that would be a Newton per current, because Coulomb per second would be amp, so it's a Newton per amp meter. Okay, not an ammeter, but that would be the units we would use. Newton per amp meter. Okay, that is a Tesla. Okay, now that's the SI unit that uses newtons, which are based on kilograms. If you did the CGS units, the centimeter gram second units, the magnetic field is the Gauss, named after good old Frederick Gauss, was that it? Whatever his name is, I can't remember. I believe it is. Great, very famous mathematician and physicist. Many, many, many areas. Okay? And by the way, 1 Tesla is equal to 10 to the 4th Gauss. 1 Tesla is 10 to the 4th Gauss. That accounts for the 10 to the third you get from going from kilogram to grams, and then the meter to centimeter would give you 2 more. So how do you come up with the third? I mean, the one remaining. Seems like that would be the 10th to the 5th or the 10th to the 3rd. Oh, okay, right. You have a Newton in centimeters here. The Newton is a kilogram centimeter, kilogram meter per second squared. You have to convert the Newton and the meters, and those go in different directions. No, the same direction. But then you're dividing by meters per second. So, yeah. This would be 10 to the, this would be a total of 10 to the 5th, and then divide by 1 gives you 10 to the 4th. So, yeah, 10 to the 4th counts. Now, they may do this on, oh, here we go. They introduced this other thing of a Weber, W-E-B-E-R. Now, we haven't run into the guy named Weber, but there was one because it's capitalized, and that, they don't tell you what that is, except that a Tesla is a Weber per meter squared, okay? You can back off and see what a Weber is. But why wouldn't they have used W for Weber?
Watts.
Yeah, they've already reserved W for watt. So since it's another guy named whose name starts with W, they have to use a WB. And then the CGS unit is Gauss, which is 10 to the 4th. Gauss makes 1 Tesla. So Gauss is a much smaller unit. Tesla is a bigger unit, but uses a smaller number. Okay. What's that? Are we doing lab today? We're not nearly through with the chapter, so we're going to have to, so today's probably going to be chapter only. We'll see. Yeah, we got quite a bit of chapter to go yet. So I have a feeling we'll even be starting next class with chapter before we get to lab. Wow. 10 sections here. We're in section 3, but the later ones are shorter. Okay. So there's your units of magnetic field. Tesla, CGS unit being Gauss. Now, they do give a couple of examples here. Let me see. Yeah. A conventional laboratory magnets, which are quite strong, would be 25,000 Gauss, but because it's 10 to the 4th, move the decimal 4 places, you get 2.5 Tesla. Those are strong magnets, okay? For permanent magnets, those are very strong. Superconducting magnets, okay, which are much stronger than that, 300,000 Gauss, moving this decimal 4 places, that gives you 30 Tesla. That's about as strong as you can get. The Earth's magnetic field, though, about 5/10 of a Gauss, half of a Gauss. So that's really weak compared to the others. That's 5 times 10 to the minus 5 Tesla. Now, what they didn't mention here is electromagnets, whereas a permanent magnet will go up to about 2.5 Tesla. You might get up to 3. I don't know if they've gotten any that strong, perhaps. Certainly no more than 5 or 6. Whereas your electromagnets, they can go up pretty close to this. I don't know, they may even be able to exceed that, 30 Tesla or so. But permanent magnets, you will never find that strong. Okay? Now, Forces are vector quantities. Now let me go back to something here. Here it is. When you see a formula like this, I want to remind you. Remember back when we did work from force times displacement? You remember that? Work was force times displacement times the cosine of the angle in between. Whenever you're using cosine, you're taking vectors that are close to the same direction. Okay? Because remember, if your force was perpendicular to your displacement, you did no work. Because cosine, that would be a 0. Okay? Cosine of 90 is 0. When you've got a sine in there, that means you're starting with perpendicular matters and going from there. So this then tells me, Q is a scalar quantity. Charge is a scalar quantity. Velocity is a vector quantity. Field is a vector quantity. Magnetic field is a vector quantity. Since you're dealing with the sine of the theta, that gives you a force which is a vector quantity. Now you're talking about a cross product, not a scalar product, the dot product. Dot product of two vectors becomes a scalar. The cross product becomes a vector.
So you're saying you have to do two different formulas to get the right answer?
No, I was just saying there's different things that you're dealing with here. That's a vector, that's a vector, this is a vector. This has to be a cross product, not a scalar product. When you're dealing with work was force times displacement. Both of these are vector quantities, but work is a scalar. Then you use force times displacement times the cosine of the angle in between. Whenever you use cosine, that means you've got a dot product, a scalar answer. When you use sine, that means you've got a cross product, which is a vector. Okay? Now, I was just mentioning that because that's going to come up again. And it comes up right here. Okay? Finding the direction of a magnetic force, we got the magnitude by QVB sine theta. That gave you the magnitude, it didn't give you the direction. Experiments show that the direction of magnetic force is always perpendicular to both V and B. Now V and B may not be perpendicular, but if V is like this and B is like that, the force is perpendicular to both of those. Okay? If they're like this, it's that way. It's perpendicular to both of those. F max occurs when the particle's motion is perpendicular to the field. V is this way, velocity is that way. That's when you get the maximum force. Force is 0 when the particle's motion is parallel to the field. You get no magnetic force at all. Okay? So if your V is this way and your V is that way, here's what you do. It's called the right-hand rule. You point your fingers of your right hand in the direction of V, yes, okay, and twist the fingers in the direction of B, that gives you your force in that direction. If V is like this and B is like that, V is like this, think about that. Oh! There's a positive charge. The right-hand rule for a negative charge makes it a left-hand rule because that's going to be in the opposite direction. So this is going to be a positive charge is going to go like this, a negative charge like that. Because the force is a negative charge, you have to, the V cross V would be V cross V would be in this direction, but because it's a negative charge, the force would be in the opposite direction. Okay. So the magnetic forces oppositely charged particles moving at the same velocity in a magnetic field with opposite directions. Same velocities here, same magnitude, same direction, same magnetic field here, this force is in that direction, that one is exactly opposite because that's the positive charge, that's the negative. Okay. And the field is always, the force is always going to be perpendicular to both the velocity and the field. Okay? So if you draw your plane here in the direction of your, that contains your velocities, and your V is perpendicular to that, well, whether they're perpendicular or not, going through that, then the sine of the angle between V and V, that's what determines the magnitude of the force. Okay. Or that's one of the factors in it. Okay. So right-hand rule number one. Now you are doing it like this. Is that right? Okay. Is this? Okay. Would this be V, B, F? Yeah, that would be right. V, B, F. Yeah. They all have to be perpendicular to each other. Well, V and B don't have to be perpendicular, okay? But these two have to be perpendicular to both of those. So point your fingers in the direction of the velocity. Start with that. Okay, that has to be going into the board. Curl the fingers of your right hand in the direction of the magnetic field. Then the force on a positive charge would be due up, straight up. Your thumb points in the direction of the force of the positive charge. If it's a negative charge, point it opposite direction. So point your fingers of your right hand in the direction of V, curl them toward the direction of B, then your thumb is going to point in the direction of the force. If it's a positive charge. The opposite of that would be if it's a negative charge. Make sense? So the force on the negative charge, if the charge is negative rather than positive, the force is directed opposite that obtained from the right-hand rule. So you could call it a left-hand rule or do the right-hand rule and then point in the opposite direction. That's what I usually do. Magnetic forces on oppositely charged particles moving. Yeah, so that's the same thing as the last one. So the magnetic force on a current-carrying conductor, the force is exerted on a current-carrying wire placed in a magnetic field. The current is a collection of many charged particles all in motion. The direction of the force is given by the right-hand rule number one. Okay? Now, what current do we use here? You folks that did the last lab. If you're using right-hand rule number one. Remember, we had two types of currents. You did that on your second illustration. Y'all were there, you did it. Second. What current do you use for determining the force given? If you're using the right-hand rule number one. Right-hand rule number one is based on a positive charge. Okay, yeah, that's where it's coming from. You call that the conventional current, not the electron current, the conventional current. So that would be, you use the conventional current there. The one going from high potential to low potential, long line to the slope. Yeah. Okay, so what would be the force on a wire? The green X's indicate that the magnetic field is directed into the page. Now here's the sort of the convention on that. If the magnetic field is into the page, picture that as an arrow, right? The arrow has a point going in and it has the feathers crossed like this. So that's the tail end sticking out. So this is to be into the page. Okay? The velocity here, if your current is zero, there is no force on that wire because there's no moving charge, no velocity of the charge. So the green arrows indicate the magnetic field is into the page. X represents the tail of the arrow. The green dots would be used to represent the field coming out of the page. So if that were flipped around and the V was in, you'd have green dots there rather than green X's. That would be coming out of this page. That dot represents the head of the arrow. Okay? The point you might make. In this case, there is no current, so there is no force. You have to have a velocity of your charge to have that. And if I is 0, the velocity of the charge is 0. Okay? And there's no current in the wire remains vertical. Okay. Now, B is into the page again, but now you've got current going this way. What current is that? Conventional current, not the electron current, conventional current. So now your velocity is up like this. B is into the page. So velocity up, into the page, the wire is bent this way. And it enters that field because the force is pushing it in that direction. Up here where there is no field, or down here there is not, it's just that the wire is being pushed here. We're just having to connect that. Okay? Current is up the page, meaning the positive charges, if there were positive charges moving, they would be moving upward to the forces to the left. Because B, the forces to the left. Right-hand rule. Now, again, the B is into the page, but now the current is down, meaning the positive charge would be going down if it was. So the velocity is down, the current is into the page, that means the force is to the right, bending the wire that way. So current down the page, the force is to the right. Always perpendicular to both the current and the field. The magnetic force, B, exerted on each moving charge in the wire. Every charge feels that. The total force is the sum of all the magnetic forces on all the individual charges producing current. So then we have B is equal to B, that's your field strength, magnetic field strength, I, which is your charge per time, L is the, this is sort of bad, they haven't listed it here. You're going to have to get that from the book. Whoa! Got to back up and hit a quick quiz. Okay, I've gone a little too far. Let's hang on a moment. Let's go back to quick quiz 1 and 2. I'm sorry. Been talking all day and my throat's hurting. A charged particle moves in a straight line through a region in space. Charged particle moving in a straight line through a region in space. Which of the following answers must be true? Assume that any other fields are negligible. Okay? The charged particle is moving in a straight line through a region in space. The magnetic field, A, has a magnitude of 0. Must that be true? Not necessarily. B, the magnetic field has a 0 component perpendicular to the particle's velocity. Yes, that one must be true. If it didn't have a 0 component perpendicular, then it would be bending. It has a 0 component parallel to the particle's velocity. Wait a minute. Let me go back and rephrase those. The magnetic field must have a 0 component perpendicular to the particle's velocity. That would be true because it's the perpendicular component. If it had a 0 component parallel to the particle's velocity, then whatever field it had, it would bend it. So I think that one has to be B. Let's go to the back and see if it's B. Quick quiz 19.1. Flip a page more. Okay, 19.1. Oh, here it is. That indeed is B. Okay, looking at 18. 19.2. The north pole end of a bar magnet is held near a stationary, positively charged piece of plastic. So here's the north pole end held near a stationary, positively charged piece of plastic. Is the plastic attracted, repelled, or unaffected by the magnet? The north pole end of a bar magnet is held near a stationary, positively charged piece of plastic. Is the plastic attracted, repelled, or unaffected by the magnet? A, B, or C? Attracted, repelled, or unaffected? Second? I couldn't hear. Okay?
No. Okay, repelled. No, the other option.
Unaffected. Okay, and why? The bar magnet is held, not moving. The stationary positively charged piece of plastic is not moving. It has to be a moving charge to be affected by a magnetic field. So that should be C. And sure enough, 2 is C. All right. All right. Now, I'm kind of at a loss here because the new edition of the book does not have this formula in it. Okay? That I found yet. Here is one place where it does show up. That L, that's the thing I'm trying to find. Okay. I'm going to come back to this in a minute. Nope. I do not see I can't find this figure, okay, on the slide. If L is some length of a wire, okay, that's what the L is, okay. So the force on the wire, so let's go back to this picture here. The L would be the length of that wire from down here to up here. That would be the length of the wire. At least that's my interpretation. It may be only the length over which it is in the field. That's not real clear here. I think it's the length in the field, but I can't say that for sure. They haven't labeled it anywhere. They didn't label it here or here. But that's the length of the wire, but whether it's the length in the field or the length total, I don't know. I think it has to be the length in the field. Okay? Now, so that's what the L is. So it's, the Q is incorporated in I because it's charge per second, coulombs per second. B is the magnetic field strength. L is the length, okay? And you see the L per second, that was the velocity. So it used to be Q, V sine theta. They just rearranged this to make it I, which is Q over time. And so rather than having V, which is length over time, so this is the length of path that's transferred, that is covered in that second. And then there's the field strength, times the sine of theta. Where theta is the angle between V and the direction of the current, okay? And the direction is found by the right-hand rule, placing the fingers in the direction of I rather than in the direction of V. That's what we were doing. They're just now telling us what, that's why it's okay to do, okay? So I takes the place of, but see, I is not a vector. It should be L, okay, in the direction of I, but we'll, that's fine. Okay. Now, that then leads to the torque in a current loop. Now, torque, by the way, is a vector quantity. I don't know if you remember this from 201, but torque is a vector quantity. Okay? And what have we got here? You got the B, which is the field strength, I, which is current, which is charge per time, A, which is the area, okay? It's not telling you what it's the area of, so we're going to have to find that out. I believe it's the area of the cross section of the wire. Okay, can't say that for absolutely certain, but I think that is. N is the number of turns in the coil. Okay, and sine theta, of course, that would be the angle between the current and the field. Okay. And torque has a maximum value. Why they changed the order around? N times B times I times A when theta is equal to 90 degrees, because that's when the sine is a maximum. Now, why didn't they leave it B-I-A-N? I don't know. N-B-I-A. Torque is 0 when the field is parallel to the plane of the loop. Okay? Now, if B is at an angle theta, there it should be, okay? And the plane of the loop, okay? If that's the axis of your loop that you've got going here, that's the axis of it, then the angle theta is this from normal to that plane to B. That will be your angle theta, and that's what you do the sine of. If that sine was 90 degrees, if that loop was like this, okay, that coil was just like that, that would give you maximum force, maximum torque. If it's along the B, in other words, if you flip this all the way here, then the B is in this direction, but so is your area measurement, that you're using there. Then that would give you 0 torque. So if B is the angle at an angle theta with a line perpendicular to the plane of the loop, the magnitude of the torque is given by B I A sine theta. Then if you have a bunch of loops, then that's where the N comes in. The torque is 0 when the field is parallel to the plane of the loop. Now, what does that mean? That if you have the angle like this is perpendicular to the coil, okay, and that calls with your B, your current is this way. By the way, current, this is the tail end of the current. The red is usually your electric field, or let's call it current. And this is point. So the current is going like this, okay, like that. And B is like this, okay. Then the force let's take this in. The current is coming out, and the V is that way, so then your force is upward. If the current is going that way, okay, so current is this way, field is that way, then the force is down. So that's what creates a torque here. Now notice what the torque's trying to do. It's trying to get that to line up with V. That gives you, will give you 0, so it's always trying to create that, to get that to line up. So if V is an angle perpendicular to the plane, the magnitude of the torque is VIA times the sine of theta. Okay. Now,
Are you taking rule again?
what's that?
You gonna take rule again?
Okay. We started at 5:30. Okay, so it's now 7:30. Yeah, so 9. This is the time to take it. FA left beforehand. It looked like she did. Tia didn't make it in today. Megan is still here. Shakina left already. Courtney's still here. Sam's still here. And Brianna's still here. Okay. Pardon me? We can have up to 10 minutes. Let's not go. Or okay, we can take a break if you want to, but that means we go till 9. If you use 10 minutes of the break, that means we go to 9. If you take less than that, okay. So let's take a break. Okay. I think the slides are doing a less than perfect job of defining all these features, okay? And one of the problems is the slides are not keeping up exactly with what is in the new edition of the book. I think I see why. The 19.4 in the book is motion of a charged particle in a magnetic field. A particle in a magnetic field. This is talking about torque on a current loop, force on a wire, okay? The force on the wire, or charge-carrying conductor, that's 19.5 here. So that's one reason it's a little out of whack here, is that 19.4, the motion of a charged particle, I'm trying to see where that is. Let's see if we can find that. No, I cannot see it. Okay, so I think what we need to do, I was following the slides and I probably shouldn't have been. Okay. Let me sort of fill in some blanks here. We had that formula, and that was back in 19.3, and that was page 624. And we did our quick quizzes there. I can't find anything in the slide set that corresponds with 19.4, so let me fill in those blanks a little bit. Okay? The magnetic force let me start over. Consider the case of a positively charged particle. Particle now moving in a uniform magnetic field so that the direction of the particle's velocity is perpendicular to the field. Velocity perpendicular to the field, that means you're going to have the maximum force, okay? And I wish, do y'all have books? Or you have e-books or what? Nothing. Okay. Okay. Uh-oh. We're in trouble now, huh? Okay. All right. Let me draw sort of what they've got here. Remember, I'm going to try to even color code it well. What we have here is a uniform magnetic field represented going into the page here. They should be uniformly spaced, mine are not, but you get the general idea. The magnetic field going into the page. Okay? We have a positively charged charge, okay, that is out here. We're going to do that in red. Okay. Here is a positively charged charge. Okay. It's going perpendicular to the field, that's its velocity. That's also a vector. Okay. Now, velocity moving this way, field moving into the page, that means the force is perpendicular to both of those. So the force, and they do the force sort of in a blue color, so we'll make it, is it blue or lavender? I think maybe lavender. Okay, purple. That will be perpendicular to both of those. There's your force. Okay, also a vector quantity. Okay, now we're going back to F is equal to Q V B times the sine of theta, the one we had before. Okay, so that's the force. Okay, now with that in mind, that is going to make the charge here go in sort of a circular type fashion, so that when the charge gets down here, red again, it didn't pick, there it goes, down here, positively charged, now it's going in that direction. Okay, that's your velocity now. Okay, and V cross, I'm going to break my arm here, V is pointing up this way. So your force, lavender force, is in this direction. Okay, and it keeps on going, and basically what you wind up with is a charge moving around in a circular path, because it's a constant velocity, perpendicular to the thing, always points to the center of the circle, so that has a circular path. So that would be what you have then. Now, so this QV and the sine of theta, your theta is always perpendicular, so that's going to be 1. So your QVB, and we'll just deal with the magnitudes now, that is going to be centripetal force. Well, your centripetal force is mv squared over r, where this is, r is the radius of that circle. Okay? Now, that's what they're going by. Let's solve that for r and see what the radius of that circle is. So multiply both sides by r and divide by this stuff. So you have mv squared over q v b, but this v cancels one of those out, so the r is mv over qb. Okay, and that's where they get their equation 19.5. Now, I don't know if you notice it or not, and I don't know that it really matters, but that's the momentum of the particle, mv, divided by qv, which is your charge and your magnetic field strength. Okay? So that's the radius of that circular path you have. Okay. I don't know if that was necessary, but that was the part that was left out completely. Okay? Then we had, we've gone through all these. And then we have on the top of page 630, we have these three figures. Okay? And that's where the formula then at the bottom of the page, 19.6, or 19.7 actually, this is 19.7. And that's where I was having trouble figuring out where it was, but again, they don't have the figure here, which makes it sort of hard to see. Okay? Now let me try to draw this one. I was looking for it all over the place here. I can't find it. So here we have a wire in the presence of a magnetic field, a uniform magnetic field, again into the page. Okay? And you have a positive charge going down the wire, which, you know, by reality is probably not too realistic. There's the velocity down the thing. This is V sub D. V sub D. Now I know what that usually stands for, drift velocity. Let's see, make sure that is what they're talking about here. And from what I said before, my guess was the length of this wire is the length of the wire in the magnetic field, so this is that L, the length of the wire in the magnetic field, okay, which is what I thought it was supposed to be. Now, what I'm trying to find here is where they label V sub D. And I haven't seen that yet. But before we get too carried away, I just noticed we skipped a quick quiz. 19.3. As a charged particle moves freely in the circular path like this, okay? As a charged particle moves freely in a circular path in the presence of a constant magnetic field, like that, perpendicular to the particle's velocity, like that, okay? The particle's kinetic energy, A, remains constant, B, increases, or C, decreases. The particle's kinetic energy, does it remain constant, increase, or decrease? Okay? Charged particle moving freely in a circular path in the presence of a constant magnetic field applied perpendicular to the particle's velocity. The particle's kinetic energy, A, remains constant, B, increases, or C, decreases. What do you think? Okay? Say again?
Is it increase?
Increase. Okay, let's see if it does. Now, certainly the mass isn't going to increase, so if the kinetic energy is going to increase, that means the velocity would be increased. Okay, now, what would create the velocity, make it want to increase? If you multiply both sides here by QV, the divide by M. Q isn't changing, and M's not changing. They told us it was an unchanging magnetic field. That was in the problem. In the presence of a constant magnetic field. So that's not changing. So really, there'd be nothing to make it change except the R, but the R is the product of the system. From this formula, I would say it should be unchanging. A. Let's see what they say. It may be right. 3 is indeed A, unchanging. Okay? All right. Now, let's go back to this. I'm still trying to find what VD, there it is. VD is the drift velocity of the charge. Okay? That's exactly what I thought it was. It usually represents that. So that's the drift velocity of the charge. Okay? Usually a pretty small quantity. Okay? Let me go and mark. This is B into the page. Drift velocity in that direction. And so this gives you the force maximum. Okay. Boy, they throw so many things in here at once. Let me give you this force, the maximum force, this is magnitude now, is QVD, that's the drift velocity, times B, okay? Now that would be of each charge, okay? But you have N, which is the number of charges per unit volume, times A, which is a cross-sectional area of that wire. So this is your A here. And L is the length of the wire. So this gives you the volume of the wire. So this is the, this would be of each charge. And that would be the number of charges. This is number of charges per volume times the volume. So that gives you the number of charges. So that's where those numbers come from. Now, they start whittling away at that, and they say that I, the current, is equal to the number of charges times the magnitude of the charge times the drift velocity times your area. Okay, now where did that come from? Charge is, or current is charge per unit area. The Q is individual charge. In VA, the V is meters per second, remember? So the Q is charge per second. So this is number of charge times, this basically is your L, okay? L per, that length per second times that. That would give you the I. So if then you replace this, that, this, and that, then you get B, A, I. Okay? Wrong. No, I took out the A. Sorry. took out the A and you had L, sorry, L. I'm sorry, I wiped out the wrong one. Leave the L in there and be Li. Yeah, that's what we've got here. Okay? Now, that's if they're in the same direction or perpendicular to each other, velocity perpendicular. If they're not in the same direction, then all you do is add the sine of theta in there. So sine theta if they're at an angle with each other. Okay. And that's the formula 19.7. Okay. Now, that's the part they had skipped. Okay. Here is where we get the torque. It was 19.5 on the old slide set, 19.6 in here. Okay, let me make sure I haven't. No, I haven't. Okay. So, these two forces that you see here, the force 1 and force 2, both of those are B being field strength, times I, which is current, times little b, and where have they defined what little b is? Oh, these are lengths. Okay, they're not showing the figure they have here, so all right, they don't show that, so forget that. If you have a circular one, this is the C part of this. They don't show A and B, okay? So this maximum torque then is B I A N sine theta. So this is your equation 1910A, this one up here, that's 1910A. And then when you, 1910A. And then when you include the magnetic moment, okay, which is IAN, so the magnetic moment, mu, is IAN. That's this part is replaced by mu, so then you get torque is equal to mu B times the sine of theta. That's your 1910B. Finally. Let's pick up with quick quiz 19.4. This is actually at the right place now. A square and a circular loop of the same area lie in the XY plane. I wish you had your book. Okay? I'm going to do it here. Okay? Actually, those last couple of formulas I did, there was the mu is IAN, and there's the tau is equal to mu B sine theta. I just did those on the last page. Here they are here. So let's just make sure they don't have this. No, they don't. Okay. A square and a circular loop of the same area lie in the XY plane. So this is going to be the XY plane, and here is our square, and here is our circle. Now, mine don't look like they are true, but let's say the area of these two is the same. Area and area are the same here. Okay? Where there is a uniform magnetic field pointing at some angle theta with respect to the positive z direction. Okay? So that's going to be hard to illustrate here. Let me get my green here. Okay, so B is going kind of into the page like this. Okay, at some angle theta with the z-axis. So if z is coming up, this is some angle theta with the z-axis. Okay? Each loop carries the same current in the same direction. Okay, so let's get our current here, I. Red is so hard to get it to come up. There we go. Okay, so let's just make it counterclockwise. There's your I, and here's the I. Okay? Same current, same direction. Which magnetic torque is larger? Okay? Now remember what the torque is. Mu, which is the magnetic moment. Okay? Everything that we've done before these formulas here say B, which is the same, I, which is the same, A, which is the same, N. Now, there really isn't anything that I can see that N has to do with anything here. The number of turns, so we're assuming one turn, so that's the same. Sine theta, it looks like to me that the torque are the same. It looks like that would have to be C, or more information is needed, could be, but this is 19.4, and sure enough, that is C. They are the same, because all of the inputs were the same. The current's the same, the area is the same, the B's the same, the sine theta is the same, everything's the same, so the torques would have to be the same. Okay. So the vector mu, and that is a vector, is called the magnetic moment of the coil. Makes you think maybe of the dielectric, because that had a moment too. Okay, its magnitude is given, mu is IAN, current, area, and number of turns. The vector always points perpendicular to the plane of the loop, so that mu is always perpendicular to the plane of the loop or loops. The angle between the moment is between the moment and the field. Okay, so the moment is perpendicular to the loops, and the field is however it's going through them. The equation for the magnetic moment, magnetic torque, is then tau is equal to mu b times the sine of theta. So mu takes all the rest of it into account. So let's now look at an electric motor. This is 19.6.1. Okay? Electric motor converts electrical energy to mechanical energy. So, in other words, you have electric current happening, okay? And the current is in the presence of a strong magnetic field, and in the presence of that strong magnetic field, it creates a torque, okay? Now, the current is going through like this, okay? Now, you happen to have here what they call a split ring commutator, okay? You have brushes here. They look like they're solid, but they're really brushes there. And as it turns, and the reason that it turns is that you have current flowing through there. The current is a moving charge in the presence of a magnetic field that produces a torque, making it turn, so that's what converts the electrical energy into mechanical energy, the turning. And the current moving in this direction and the field in that direction, basically perpendicular to each other, then I cross B, okay, is going to be a torque that's twisting this way, okay? This is not a very clear illustration here, but it does twist this way. So it's trying to line up so that the current and the field are parallel with each other. That's what it's trying to do. But as soon as it gets close to this, then the split ring commutator reverses direction of the current, and then it tries to twist another half current. So that's what's happening, and that's why this is occurring. The mechanical energy is in the form of rotational kinetic energy created by the torque that you have there. The axis of rotation of the loop is in that direction. So you see what's happening this brush, so here's a positive charge going here, going through this way, making the current go like this, okay? That's going to create a twisting force like this, trying to line it up so that it will stop. But the very time that happens, then this split ring commutator happens. This side then becomes the one, and then the current reverses the other way and takes it another half turn, another half turn, another half turn. Every time it goes half a turn, the split ring commutator reverses the current on it again, keeping it turning with a pretty constant torque. Okay? So, that's what's happening there, the electric motor. The electric motor consists of a rigid current-carrying loop that rotates when placed in a magnetic field. The torque acting on the loop will tend to rotate the loop to smaller values of theta until the torque becomes zero if theta equals zero. If the loop turns past that point and the current remains the same direction, the torque reverses and it just does this, okay? But if you have that split ring commutator, then it reverses the current and it keeps going in the same direction then, and that's what it's all based on. To provide continuous rotation in one direction, the current loop must periodically reverse, and in AC motors that reversal naturally occurs. In DC motors, a split ring commutator and brushes are used, and the actual motors would contain many current loops and commutators, so it keeps it running very, very smoothly. You don't have more torque at one time and less at another. You have many of them, and that keeps it running very, very smoothly. Okay. Just as the loop becomes perpendicular to the magnetic field and the torque would become zero, inertia carries the loop forward and the brushes cross the gaps of the ring, causing the current loop to reverse. That provides more torque to continue the rotation. The process repeats itself every half turn. It changes the direction of the current, which keeps it turning in the same direction. Okay. Now, here's now, sorry about this. Let's go back several pages. Sorry about this. There's the figure 19.9. Okay. Obviously, they've rearranged the order of this. This is forces on a charged particle in a magnetic field. This is the one I tried to draw earlier. It's a pretty picture here, so let's take a look at it. Consider a particle moving in an external magnetic field so that its velocity is perpendicular to the field, just like we were describing before. The force is then always toward the center of the circular path. The magnetic force causes centrifugal acceleration, changing the direction of the velocity of the particle. So the force F is acting always toward the center of the circle. And this would then be the radius R. We already did this when the B is into the field. So this is the figure we were talking about before. Sorry about that. Okay. Equating the magnetic and centripetal forces, we did that too. And solving for R, we did that. Where R is proportional to the moment, the momentum of the particle, that's mv, inversely proportional to the magnetic field, and sometimes that's called the cyclotron equation. Okay? The greater the momentum, the larger the radius, and the more it's spinning outward. Okay? And in the presence of a constant field. Okay. What if the particle's velocity was not quite perpendicular to the field? Okay? Then the path becomes a spiral, not a circle just going that way. The spiral path is called a helix. Here you have a velocity component that has one component down the field, the other component perpendicular to it. The down the field component makes it keep going further and further down the field, making this helical path. Okay? And then you have motion that goes like that. Path is called a helix. That's where the term helical path comes from. Okay? Now, trying to keep up with the text here. Okay, I don't see Hans Christian Ørsted anywhere here, so I'll just go on and mention him. Hans Christian Ørsted lived 1777 to 1851. What was that approximately in terms of us here in the U.S.?
The very beginning.
Very beginning. That is right after the Declaration of Independence. Next year he was born, so he didn't know much about that. And it went right up until very close to the war between the states. Okay? So he lived, what was that, 51 and 23, that would be about 74 years. Pretty good for that age. Best known for observing that a compass needle deflects when placed near a wire carrying a current. Okay? So basically, if a wire is carrying a current, it creates a magnetic field. That's what deflects the compass needle. First evidence of a connection between electric and magnetic phenomena. Before that, they knew of none. So he was the first to do that. Hans Christian Ørsted. If I'm not mistaken, he was Dutch, I believe. I'm pretty sure of that. I don't believe it was Danish. I always get those crossed up. Yes, and this is 1907 is where we're beginning this. However, the title is Ampere's Law, which we haven't gotten there yet. Okay. So let's look at the magnetic fields in long, straight wires. A current-carrying wire, okay, produces a magnetic field. Why do you think a current-carrying wire produces a magnetic field? What we said earlier about the spinning of the earth and everything else, a moving charge induces a magnetic field, and if a wire is carrying a current, that means it's producing a magnetic field. Now, what kind of current would that be? We haven't really talked about this much. We're talking about direct current. Alternating current, a field would be changing just as rapidly as that, which would be basically canceling itself out. So we're talking about direct current. Produces a magnetic field because you have a moving charge moving in one direction. The compass needle deflects in the direction tangent to the circle. If you put little compasses around here, you see they always follow the path of the circle, meaning you've got a magnetic field going in that direction. That's your beat. Okay? The compass needle points in the direction of the magnetic field produced by the current. Okay? When the wire carrying a strong current, the compass needle deflects in directions tangent to the circle, pointing in the direction of the bead you confirm. We've already said that. Notice there, strong current, meaning you need a pretty good voltage across it to produce a strong current. Okay? You get a lot of current, that wire's going to get hot. So we don't usually do this much in the lab. Otherwise, we'd be burning things up. But that would produce a measurable magnetic field. We just aren't going to do too much with that. Okay. The picture before here, if you had your book and there was no current going through that wire, all those compass needles would be pointing to the north because there wouldn't be any other field affecting them except the Earth's gravitational field. Earth's magnetic field. Okay. Now, direction of the field of a long, straight wire. Okay? This is a second right-hand rule. Okay? And here's what you do. Grasp the wire in with your right hand. Point your thumb in the direction of the current. Which current are we talking about here? Which? I can't hear. It's direct current, yeah. But which of the direct currents? Conventional or electron? Remember the last lab?
Conventional.
Conventional. The direction of positive charge would move if it was moving. Okay, when you grasp the wire with your thumb pointing in the direction of the current, then your fingers are going to point in the direction of the magnetic field. Always. Okay? Grasp the wire, point your thumb, the fingers will curl in the direction of the magnetic field. Okay? That's your second right-hand rule. The first one was the direction of the force due to cross products. This is the direction of field due to a moving charge or a current in a long straight wire. Okay. And by the way, I hadn't noticed this before. I'm pretty sure it wasn't in the older edition of the book. But they have a picture here, figure 1922, the engine compartment of a Toyota Prius hybrid vehicle, which basically is an electric generator, okay, producing charge being stored in a battery, producing energy being stored in a battery. Okay, what is the magnitude of this field of a long straight wire? Okay, this is the formula 1911 that you see on page 636. Okay, the magnitude of the field at a distance r from a wire carrying a current of I is the B is mu naught I over 2 pi r. 2 pi r is the circumference of that circle, okay? Mu naught is 4 pi times 10 to the minus 7 Tesla meters per amp. That's called the permeability of free space, okay? Now, just because I feel like I've got to say this, and I'm pretty confident of it. The mu naught here I don't think has anything to do with the mu, which is our magnetic moment. I don't think the units are the same. I don't think anything really matters there. This is just a constant of nature, the permeability of free space. Now earlier we had a permittivity of free space when we talked about electric fields. That was epsilon naught, or epsilon, I don't remember which we called it. This is mu naught, which is permeability of free space, which is Tesla meters per amp, which is field strength divided by, multiplied by distance divided by amp. Now, the reason for that is pretty clear, I hope you see, because if you solve for mu, okay, you would have to multiply by 2 pi r. Well, 2 pi has no units, but r has a unit of meters. So B is in Tesla, so there's your Tesla meters, and then you're dividing that by I, which is current, measured in amps. So yeah, the units make sense. Mu naught is called the permeability of free space. Not real clear why they call it permeability, but they do. Okay. Here's another good-looking character, huh? This is Andre Marie Ampere. Okay. Now I have to correct myself here. I was under the impression he lived about the same time Franklin was in France. Not so. Possibly Coulomb did, but not Ampere. Look at that. 1775 to 1836. He was born a year before Oersted, 2 years before Oersted, and died something like 14 years before Oersted. So he didn't live nearly as long as 25 and 36 would be 61. He's credited with the discovery of electromagnetism. Okay? Oersted noticed the relationship between, the link between electricity and magnetism, but the ampere established the relationship between electric currents and magnetic fields. So he took it a step further than Oersted did. So Oersted, even though he was 2 years younger, discovered it. Ampere did something with it. He established it. He was French. Oersted, I think, was Dutch. Okay. And I don't see ampere
so
anywhere.
Was dumb compared to him.
What's that?
So Oersted was dumb compared to him.
Dumb? Well, he didn't take it as far, but he discovered it sooner, even though he was younger. So they worked together. I mean, not that they actually worked together, but one built on the other. Okay. So you might say Oersted didn't recognize what he had. I don't know. So anyway, the reason they mention him is to lead into Ampere's law. Okay? That equation 911, which we just had here, that's this one, B is equal to mu naught I over 2 pi r. Okay? Enables us to calculate the magnetic field due to a long straight wire carrying a current. A general procedure for deriving such equations was proposed by the French scientist, there's Oersted. He's in just a little blue box, not a picture of him. Danish, I said it was either Dutch or Danish. It turned out he was Danish, physicist and chemist. Oersted is best known for observing that a compass needle deflects when placed near a wire carrying a current. This important discovery was first evidence of the connection between electric and magnetic phenomena. Oersted was the first to prepare pure aluminum. So you see, he was a chemist as well, not really as interested in the physics. Whereas André-Marie Ampère, even though he was 2 years older than Oersted, didn't live as long, a Frenchman credited with discovery of electromagnetism, the relationship between electric currents and magnetic fields. So he built on what Oersted observed. Okay? And this then, Ampère found a procedure for deriving the relationship between the current and arbitrarily shaped wire and the magnetic field produced by the wire. And here is Ampere's circuital law, often referred to as Ampere's law. The sum of all the magnetic field parallel to your coils, and this would be the length that you would do, sum of all the magnetic field parallel to the length of the wire is equal to that mu naught, the permeability of free space, times the current. You sum over a closed path. Okay? Now, here is the figure you see on page 637, top of the page. It doesn't matter what path it is. Choose any arbitrary closed path around the circuit. It doesn't have to be regular. It doesn't have to be circular. It doesn't have to be just any closed path around the current. The current is moving upward. Sum all the products of the B parallel to that path and times the delta L. Okay? Now, here is your B. Looks like it's pretty much perpendicular to the wire. And the B parallel times L would be the, if this is your, right there, that happens to be your delta L. The B's that are parallel to that delta L, there, you sum all those all the way around here. Okay? Sum all those around. Then you'll get the mu naught times the current. Okay? Now let's go back and look at those units again. Mu naught is Tesla meter per amp. Okay, Tesla meter per amp. Your Tesla comes from your B. The meters come from your delta L, and divide by I, and you get your amp, Tesla meter per amp. Yeah, so multiply by the current, and you get the summation of your B parallel with the delta L's. Sum over the entire closed path, and that gives you a measure for the current. Okay? And from that, they named the current after ampere. Okay, the unit for current. Okay. And it takes us back to the same formula we had before there. Okay. There it is again. B is equal to mu naught I over 2 pi r. Same as we had before, which then it was just a field around the current carrying wire, which is the same that we have here. If you have a long straight wire, use a closed circular path. The circumference of the wire is 2 pi r, that's the distance around it. So your B is mu naught I divided by 2 pi r. Identical to the result previously obtained, just like I said. Okay. Now, that moves to 19.8, magnetic force between two parallel conductors. Okay. So what we have here, we have two wires here carrying two currents. I1 that way, I2 that way. Okay? I'm guessing they intend those two wires to be parallel because they put a D distance between them, which I assume is constant as you go down. Frankly, when I'm looking at that, it looks like they're closer on the right-hand end than the left, but that's not supposed to be. Force on wire 1 is due to the current in wire 1 and the magnetic field produced by wire 2. So they don't show that, but the force on wire 1 is the current in wire 1 and the magnetic field produced by wire 2, which is this one. Okay, so yeah, I2 is this way. The magnetic field is right-hand rule. Grab the wire in the direction of the current, the thumb in the direction of the current with the right hand, and the D is going like this. Okay, and the D happens to be the distance between those two. So, with that going and the currents going in the same direction, the force on wire 1, due to its current, is pulling wire 1 toward wire 2, I2. So the force per unit length is, for a unit length L, that's what length we're talking about there, is force per unit length would be mu naught I1 times I2 divided by 2 pi d. Okay? The field B2 that we see here, wire 1 is due to the force on wire 1 given by force on wire 1 is B2, that's the magnetic field strength, times your length times your current in I1. Okay? So force per unit length is divide that by L, and you have V2, which is mu naught I2 over 2 pi r, which is D. That's not, yeah, so that works out exactly. Okay, so that gives you force per unit length. Okay. And that's the equation, top of page 639. Okay. And as you saw here, that force is pulling them down, so it's an attractive force. And here are the rules. Parallel conductors carrying currents in the same direction attract each other. Parallel conductors carrying currents in opposite directions repel each other. You just turn the things around and the force will be going in the opposite direction. Okay? This enables us then to define what an ampere is and then ultimately what a coulomb is. The force between parallel conductors can be used to define the ampere. So here's what we got. Two long parallel wires exactly 1 meter apart. That's pretty far apart, by the way, folks. Really far apart. Carry the same current, and the magnitude of that magnetic force per unit length is 2 times 10 to the minus 7 newtons per meter. That is a pretty small force. Measuring that is pretty tough, but if you don't measure that, the current is defined to be 1 amp, which is a huge amount of current, by the way. Okay? So the SI unit for charge then in a coulomb can be defined in terms of the ampere. If a conductor carries a steady current of 1 amp, which is a lot of current, then the quantity of charge that flows through that, any cross-section of 1 in 1 second, is 1 coulomb. Okay? So 1 amp is 1 coulomb per second. So that's how you define a coulomb. It seemed a little crazy to me. It seemed like coulomb would be the fundamental charge, and then a coulomb per second would be an amp, which would be a derived charge, but they do it the other way. They figure out what the current is, amp, with this weird measurement, and then multiply that by the 1 second, and you get a coulomb. Okay? Now, before we do that, before we get to magnetic field in a current loop, which is the next section, let's do the next 2 quick quizzes. 19.5. Which of the following actions would double the magnitude of the magnetic force per unit area, unit length, which, let's go back to that. This is magnetic force per unit length. Which of the following actions would double the magnitude of the magnetic force per unit length between 2 parallel current conducting wires? Choose all the correct answers. Okay, A, double one of the currents. Would that double the force per unit length? If you had 2I1 rather than I1, yeah, that would double this. Or 2I2 rather than that. Now, don't double both of them, double just one of them. That would work. So A would work. Okay? Double the distance between them. Would that double this? No, it would have it, because that distance is in the denominator. So not B. A, yes. B, no. Reduce the distance between them by half. Yeah, if you do this by half, then that flips it over and doubles that. So C would work. Okay? Double both currents. Now that would be 2 times this, 2 times that, that would be 4 times. That would increase by that 4 times. So A and C would be correct. Okay? A and C, perfect. 19.6. In figure 1928, okay, that's this figure right here. Figure 1928, I1 is 2 amps. So this is 2 amps. Okay? I2 is 6 amps. Which of the following is true? Note that F2 represents the magnitude of the force on wire 2. Okay? Would you say that F1 is equal to 3F2, this is A, F1 is equal to 3F2, these are magnitudes, B would be F1's equal to F2. C would be F1 is equal to F2 divided by 3. Okay. What you think? A, B, C. Notice they don't say which of these is which. This could be F1 or it could be F2. Mu naught, product of these two, that would be 12 over this. That would be F1 or it would be F2. They're the same. The forces are the same. F1 by F2, F2 by F1, they are identically the same. Okay? Because you use both of them to calculate the F1. Okay, so that is B. All right. (19.9) Magnetic field of current loops and solenoids. Okay, we're going to start with current loop. Magnetic field of a current loop. Here we have a current loop. This is your figure 1929. Okay, you have current flowing around like this. Okay, the strength of the magnetic field, that V1 that you see there, produced by a wire, can be enhanced by forming the wire into a loop. All the segments delta X contribute to the field, increasing its strength. Okay, now let's think about this. Hold it with the right hand, current's flowing like this. The field is coming up here, up here, up here, up here, up here, all the way around. It's going up. So this V is being contributed by every little piece here, and it's always upward. That is a current loop there. Okay, so the V1 is enhanced, far stronger than it would just be one. If this line loop was straightened out, then that would be a very small V. But now with all these contributing to it, it would be much, much bigger. Okay? So that's the reason that current loops are stronger than straight wires. In fact, straight wires, you have to have so much current before you can even measure the magnetic field. With a current loop, much easier. Okay? And here's basically the reason. It's saying the same thing I did before. The magnetic field lines for a current loop resemble those of a bar magnet. Okay? Your current, if it's going in this direction, they're all pointing upward. Okay, so all your field lines are going up, so they're acting like a north pole up here and a south pole down here. Going like that. Okay? One side of the loop acts as the north pole, the other side is the south pole. They're saying the same thing. Okay? Now, what's the difference in A and B then? Oh, I guess they've just put a bar magnet on top of it and made it look so that the lines look almost identical. Okay? Yeah, they just put a bar there as if that was a magnet. Okay. Now, the magnitude of the magnetic field at the center of a current loop with a radius capital R carrying current I is B is equal to mu naught I over 2 capital R. Okay? Now I want to scoot back a little bit. Of a single wire is this. Ampere's law to find the B of a long straight wire is mu naught I over 2 pi times little r, whatever that radius is. Okay? Compare that with what we've got now, 2 pi mu naught I over 2 capital R. Notice what? You've lost the pi in there, okay? And the reason is you got a circular loop, so all those pi's as you go all the way around, they add up, and they're in your denominator, so you lose that fraction, okay? With n loops in the coil, not just with single loop, but you have n of them. Now it's n times mu naught I over 2r, okay? So you've got an even stronger field line. Not only do you have the added from all the segments around a loop, now you have n loops, which makes it even stronger. So what do you have then? If you have a series of loops, call it a coil. Long straight wire is bent into a coil of several closely spaced loops. The resulting device is called the solenoid. A loop of wire, okay, a loop of wire is called, with several coils, is called the solenoid. Also known as electromagnet, since it acts as a magnet and it carries a current. Now, I've always thought, and maybe it's mistaken on my part, if you have an iron core through there, then you have an electromagnet. This is saying you don't really need the iron core, but this is a solenoid electromagnet, same thing. And notice here, this would be like the south pole of the magnet, there would be like the north pole of the magnet, okay? And here's the deal, folks. You have lots of coil with a reasonable amount of circuit. Remember, this shows it going in and up, it's coming out, in, out, in, out, in, out. So it's going like that. Then you can build a stronger magnet. Much stronger than any bar magnet you could possibly have. That's what I was talking about before. They get much stronger. So that's what a solenoid is. A series of coils through which you have a current flowing. Closely spaced loops, that's the solenoid. Okay. The magnetic field of a solenoid, the field lines inside the solenoid are nearly parallel, uniformly spaced, close together. That indicates the field inside the solenoid is strong and nearly uniform. The exterior field is non-uniform, much weaker than the interior, and the opposite direction to the field inside the solenoid. So if the field inside the solenoid, the lines are going up, outside they're coming down, but much weaker because the lines are much further apart. And fairly irregular too. Go back to that picture, and you see the field lines. Some of these are going around the loop, some of them are doing here. Generally very weak here, but very strong in there. And very strong at the poles too. The exterior, oh yeah, we already covered that. Okay. Here's that picture. Okay. This is the one we had back there on page way back. Way back. Wow. I believe they're this far apart. That was way back on the very first of the topic 19, on page 620. Very first figure on the page. Now we're up to 640. 20 pages ago, here's that picture. The field lines of a closely placed solenoid resemble that of a bar magnet. That's the same thing we said on the last. One end of the solenoid acts as the north pole, the other end is the south pole. Why is that picture in here? It doesn't seem like it makes a lot of sense here, except if you think about this, this is probably one huge coil of wires, a huge solenoid with a fair amount of current running through it. and that produces that, I don't even remember what they call it, the rail guns, launch projectiles at high speeds with using magnetic force, racing them down the coil, okay? And that's what produces that, okay? Now, the magnitude of the field inside the solenoid is constant at all points far from the ends. Don't get right at the ends, but all points inside, pretty far from the end. And here's the field strength, the magnetic field. Mu naught N times I. Okay? Now let's see how that differs from what we had for a single coil. You had a current loop, mu naught I over 2R, or mu naught I N over 2R. So now we'd have mu naught N I, forget the 2R, okay? That seems to have left the picture here. Mu naught N R. Now, here's the problem. This N is your little n, not your capital N. The number of turns per unit length, which would be capital N divided by L, okay? And it says you can get the same result by applying Ampere's law to the solenoid. You get the same answer. Mu naught, B is equal to mu naught, that's the permeability of free space, times the number of turns per unit length, that's capital N divided by L, multiplied by U current. Okay? So you have to know the device you're talking about to talk about its magnetic field. Okay? So here you get it from Ampere's law. The cross-sectional view of a tightly wound solenoid, really closely wound, and you assume these are very uniform lines inside going in that direction. The solenoid's going like this, and your field lines are going upward. Okay? If the solenoid is long compared to the radius, long this way compared to the radius this way, we assume that the field inside is uniform, and outside we're assuming zero. We're not getting near the ends where obviously you get some field outside, but we're assuming zero. You're a long way from the ends. Okay? Apply Ampere's law to the blue dashed rectangle. I don't see that it's blue, but here's the rectangle we're talking about. Okay? Apply Ampere's law there. Okay? It gives the same result as previously found, and that would be the total current. Go back and review Ampere's law. I was going to flick back, but I don't know if we have time for that. Yeah, it's not that many. Here's Ampere's law. No, that's not it. There's Ampere's law. Mu naught I over 2 pi r. No. Okay. Okay, here it is. Mu naught B is equal to mu naught I over delta L, basically. Okay. That's longer than I thought. Okay. Now, here you have your you have N turns per unit length, okay? That gives you your N for here. So if you have N coil per unit length, your length there is L, so you would have N N per L would be how many of these you have. Let's say 1, 2, 3, 4, 5, 6. So if that was 6, it would be 6 turns per L. So that would be your N would be 6 in this case. And these are your sides. It really doesn't matter. Your length here would be that. And your mu naught N would be N per L. And if you have length L, yeah, it basically comes out exactly the same. Okay. Now, turn back so many pages I've lost. Okay, here we go. Okay. Guess I wasn't turning the pages often enough. Okay. I'm running out of steam here. Magnetic effects of electrons and their orbits. Okay. Trying to see exactly where this is here. Okay. This is basically jumping over to 1910. Oh, I'm sorry. Go back here. Ampere's law applied to a solenoid, 1909. Here it is. There's the figure. The summation of B parallel delta L is equal to BI. The right-hand side is the total current passing through the area bounded, and that would be mu naught okay. Sort of drives me nuts. Sometimes I use the script little l and sometimes you use a capital L. I think it means the same thing here. And basically you get BL N is the number of turns per unit length L, which I think they mean the little script L here is capital L on the left. The total current through that would be B times L, and that's mu naught Ni. Divide by L, and you get mu naught N over L I, but N over L is little n. You get the same results you did before. So that's how you got this result using Ampere's law. Okay. They're a little sloppy with their notation. Okay. This is moving to 1910. Magnetic domains. Man, we came so close to finishing the chapter. I don't think we're quite going to make it. So I think we're going to start here next time. So let's...
Did you hand out test 5?
Test 5?
Yeah,
I think so.
You did? I didn't get that.
Okay. I didn't get deep enough in the stack. Still got to get deep. Okay, let me go over quickly what we're going to do next time. Okay, well, you were here last time, weren't you? Oh, yeah. It confuses me every time I see this. Here it is. I keep saying I only have page 1, but page 2 is on the back. So don't forget to flip it over. That's test 5. Okay. Now, what are we going to do next time? We'll start with 1910, and literally we only have 2 pages to go. But there's a lot in this 2 pages, so I wanted to go over it. And this is what we were talking about before, why iron, nickel, and cobalt can be magnetized and nothing else can. So all that will depend on this, 1910. So it's not going to take us long to finish that. Okay? So what we're going to do, as soon as we finish that, then we'll continue and do topic, goodness gracious, a lot of problems here. Topic 20, induced voltages and inductance. Okay, now what I have to do, Okay. Oops, I got into the wrong chapter. Okay, so we'll go on and start topic 20. Okay, once we get to the hour and a half mark, in other words, starting at 5:30, going to 7. At 7 o'clock, we'll stop and do the electromagnetism lab, which probably won't take us 2 hours, but I think it'll be fairly instructive. So we'll do that. So the first hour, we'll finish chapter 19, start chapter 20, and then we'll stop at 7 o'clock. At 7 o'clock, we will do the electromagnetism lab. I'll give you the test for chapter 19, and then, but we've already started chapter 20. So by the end of by the next time we meet, we'll finish chapter, or at least make progress on 20, and if we have a chance, then we'll have the lab on that. We'll see how it goes from there.
How many more tests do we have?
It depends. We've lost 3 Mondays so far. Memorial Day, the Monday I had to be in at the meeting in New Orleans, and then last Monday, which was a surprise. So now we're on an 8.5-week term, so I don't know how many we'll do. Remember I have to go back and check my syllabus to see for certain, but we've done topic 14, 15, 16, 17, 18, we're doing 19 now. We've got let's count backwards. Modern physics at the end, mirrors and lenses, and light reflection and refraction. So I'll have to check. I can't remember if we do 20 or not. If we do 20, then we'll do 20. But if not, we might have to back up and go on to topic 22. I'll check that before class next time. It's just been so long since I did the syllabus, I don't remember. But to answer your question, we've done 1, 2, 3, 4, 5, 6. We're on 6 now. 7, 8, 9. I think we can squeeze in 20 before the end of the chapter. We'll try to anyway.
Good night.
Good night. Have a good evening.